For this video, we're going to look at graphing a square root function. So if we look at our parent function, the most basic form of the square root function is just y equals the square root of x. So if I think about making a table, right, a table of values just to get an idea of what this graph is going to look like, I'm going to choose a couple examples to plug in, and I'm going to do some that are kind of going to help us out a little bit, because you can't really take the square root of everything. So I'm going to say, -1, 0, 1, and then I'm going to skip to 4, and then skip to 9. Alright, just some numbers to help us out. So I'm going to start with 9. I'm going to start from the bottom and work my way up. The square root of 9 is 3. The square root of 4 is 2. The square root of 1 is 1. The square root of 0 is 0. And the square root of -1 is not going to be a real number. It's going to be that imaginary number. So I'm just going to leave that one out. We can't take the square root of it. So I'm just going to plot these points. We've got 0, 0. Oops. Maybe. 1, 1. And then we skip to 4, 2. And 9, 3. And maybe. Alright, and I'm not going to have any negatives because I can't take the square root of a negative number and get a real number, so it's not going to be on my graph. So I have no negatives this way, so that means my graph is going to start at 0, 0 and go up like so. Right? We call this shape a swimmer's arm. That's how you can remember. It's going to make a swimmer's arm. And if you think about it, the square root of x is the opposite of squaring. So it's the opposite of x squared. This is actually an inverse function for our quadratic formula. Right? And so if you think about it, if we did consider our negative roots, like the square root of 9 to be 3 and -3, I would also have a graph that had part of it down here. Just a mirror image. Okay, this graph makes our parabola, but to the side. Right? This is our sideways u. Okay, so they are very similar functions, and they're inverses, so they're going to have similar shapes, but for our square root function, we just use the positive roots, so it's a swimmer's arm, so it's just above the x-axis. Our general equation, it looks very similar to what we looked at in vertex form of a quadratic. We've got those same letters a, h, and k. So our general form is just y equals a times the square root of x minus h plus k. Right? That a does the same thing it did for our quadratics. Right? It tells me which way it opens. Right? So if it goes up or if it goes down. Or in other words, it tells me if it's reflected or not. Right? A negative means it's going to be reflected going down. And it also tells me if it's stretched or compressed. So if it's going to be pulled vertically or squished vertically. So if it's going to be skinnier, kind of taller, it's going to be stretched, and that's when a is greater than 1. And it's going to be compressed if a is between 0 and 1, just like it was with our quadratics. So a tells us if it's reflected, right? If it's negative, that means it's reflected. If it's positive, that means it's not. All right, and then it's going to be either stretched or compressed based on if a is bigger than 1 or between 0 and 1. H is our horizontal translation, and it's always going to be the opposite sign, just like with our parabola, right? It's kind of, you can consider it kind of be inside parentheses, right? So it's going to have the opposite sign. And then that K is our vertical translation. It's going to have the same sign, right? And this translation, remember, everything is a translation of our parent function. So my parent function starts at 0, 0, and it goes up to the right. Right, so that means if I go left, right, up, down, I'm taking that middle point and I'm moving it based on that horizontal vertical translation. Right, so that HK point is very important for us. The HK point for a quadratic was the vertex. It's going to be very similar to this graph, but we don't really have a vertex so-called. So we're going to call it our starting point. Whatever that HK point is where our graph starts, and then we're going to do that swimmer's arm, whether it goes up or down, and stretched or compressed. So for example, I want to graph 2 times the square root of x minus 2 plus 5. So I'm going to start by finding that HK point. So remember, H is always opposite, so this would be a positive 2, and then K is the same sign, so we got positive 5. So my HK point is at 2, 5. So I'm going to go to 2, 5 on my graph and put a point. Okay, the A value is positive, so that means it's going to have that same orientation as our parent function, so it's going to go up and to the right. And then it's at positive 2, which is greater than 1, so that means it's stretched by a factor of 2. Okay, so if you think back to our quadratics, whenever we graphed in vertex form, right, we had a dotted line and a solid line. So my dotted line is what my graph would normally look like, which is something like that. Not a very good graph, but that's what it would look like if it was not stretched or compressed. I'm stretching it, so I'm making it get taller. So my sketch is going to go above it like so. We also have to look at domain and range. Remember, domain is where we have x values and range is where we have y values. So looking at my graph, I have nothing over here. I have no part of my graph is on the left side of that y-axis. So I have nothing. My graph does not start until x equals 2. And then it goes to the right forever. So that means my domain goes from 2 to positive infinity. Infinities always get a parentheses. And then I'm going to look at this value. I have a point at x equals 2, so I'm going to include it. I'm going to put a bracket. My range is the y values. I have no graph down here at the bottom. The graph does not start with the y values until y equals 5, and then it's going to go up forever. So my range is going to be 5, infinity, with a parentheses and a bracket, just like the domain. Okay, so your domain is always going to have to do with h, whatever this h value is, and then your range is always going to have to do with k. It's just a matter of if it starts at that value or if it ends at that value. And that's all we have to do to graph square roots.